Alright, so ideally we wanted to be talking about MNIST and SciFAR, which I keep mentioning by name without really describing in detail. These are data sets full of images. In order to prepare for this, I'd like to spend a little bit of time this lecture talking about classification problems, right? Because that's what we're going to be doing with these data sets full of images. And I think it might be better if we've had a little bit of time to kind of wrap our minds around some of the issues related to classification problems before we dive into MNIST directly, right? So when writing Python programs, we often think in terms of algorithms. We have a certain problem that we want to solve, we design a solution, and we break that solution down into steps, right? And we write a program that represents those steps. When working with neural networks, we think in terms of training sets and rules and input-output pairs. The task that we want the network to perform is implicit in the data set that we give it, right? Which is why designing data sets is an important task, right? Okay. So we've already performed a couple of different types of tasks. So one of them is a regression task, where we just train a network to approximate a function, known or unknown, right? And when we were training it on logical rules, that is an example of a regression task. Why did you do that? Why, LibreOffice? Why did you do this? Anyway. Right? That's regression. So another type of problem is classification. In a classification problem, we are attempting to train a network to assign each input to a given class, right? And a fairly obvious example of classification might be training a network to assign an image of a number to the actual number, right? So image recognition is a kind of classification, okay? Some other things that might be classification may not be as obvious, right? We might think of a self-driving car as a kind of classification problem because what it's kind of trying to do is learn to match a situation, right? An environment that consists of a velocity, a brake pressure, a gas pressure, and a whole bunch of other stuff, and maps that onto a control decision, right? Gas, brake, turn. We could also kind of think of this as a kind of classification problem, okay? And we've already seen a classification problem in class, right? In the homework, when we trained a network to divide the unit cube into 3 volumes, that was a classification problem. That network had each output, and each output was associated with one of the regions we were trying to get it to learn to recognize. Okay? And that looks like this, right? And I drew this in one of the classes, and I wish I had included this in the assignment or the lecture or something. But here I'm going to briefly sketch out the unit cube. Right? So here's 0, 0, 0. Here's 0, 1, 0. Here's 1, 0, 0. Here's 0, 0, 1. These are points, right? Each one of these lines is one of the axes that one of the input variables represents. So what we want it to do is we wanted it to learn to divide this unit cube into these little spheres, right? So there is the one at 0.3. And then here was the outer one at 0.6. Okay? Okay. Ooh, that was... Here we go. And then we wanted it to learn to label each one of these with a given output. So the output vector in the outermost one was 0, 0, 1. And then in the sort of next inner one was 0, 1, 0. And then in the innermost one, and I still have more colors, it is 1, 0, 0. Right? And what we see is that it is associating each one of these outputs as a label for each one of these regions, right? The first element is innermost circle, the second element is outer circle, and then the third element is the outer wailing darkness that is everywhere else, right?